Hello and welcome to another LeetCode problem. So today we're going to be doing problem number 23, merge k-sorted lists on LeetCode. And we're given an array of k-linked lists. Each linked list is sorted in ascending order. Return the linked lists in a sorted list. And so you're given these lists of linked lists, and what we have to do is we have to manually sort them. So this k value can be really big. So let's just think about how we would solve this problem in a brute force way. We'd probably have to have some kind of pointer, right, to all of these. So let's say we have like the head of every list. So let's say we have the head here, we have the head here, we have the head here. And then we just have to have some kind of while loop saying like take the smallest one out of these and put that into our list and then move that. So let's say for, how would this look like? For this, well, it would be one of these two. So let's say we put this one in. Let's just have our output array here. Or this would actually not be an output array, this would be an output list, but let's say we put a 1 here. Then let's say we move this to a 4. We have to go through the list again. 1, 2, 4. So we'd put in a 1. Okay, we move this over here. 2. This over here. Then we have a 3, 4, so 3. Move this over here. 4. Now this is over here. And then 4, 5, 6, right? And so the problem with this is our number of lists is really big. And if our number of lists is really big, we can't just keep, for every single iteration, we can't just take a look at every single one over and over and over and over and over. And so let's think of how would we make this more efficient. Well, what we could do for this is we have k-sorted lists. What we could do is we could take every single front node. So let's just say we have some data structure that holds every single node for all of these lists. Not every single node at the start. So we have some data structure that is going to hold. Let's just call this list maybe like L1, L2, L3. And then that's the front node. So we're going to have an L1 node, L2 node, L3 node, not necessarily sorted. But once we have these, what we can do is we can figure out, okay, what's the smallest one? And then we have some other lists that we're just currently chaining. So let's say we make some dummy node, right? And then we just keep adding nodes from here into this. So let's say L1 is the smallest. Well, we're going to pop out this L1, we're going to put it here. And then we're going to see, does this L1 have a next? If it does, then we put that new L1, this new L1 would be the L1 next. So let's just call this maybe like L, if this is L1, maybe let's call this L11 or whatever. And this is L10. Let's just do something, so let's just say something like that. And then we have to check all these again. Which one's the smallest? Okay, whatever it is, pop it out, put it in here again. L20 and so on, whichever one's the smallest, and then does this have a next? If it does, put it in. If not, remove it. And we have to keep doing this until this whole data structure is empty, because that means we've run out of nodes. And so what's an efficient data structure that we know that can easily compare a bunch of values? Like let's say instead of storing this node, because it's going to be hard to compare nodes unless we actually make a node comparator, but let's say instead of making a node comparator, we store a tuple or just an array of the node value and then the node itself, right? So for each of these starting nodes, we store the node value and the node itself. So what's a data structure that we know that can easily find the smallest value out of all of these? Well, it's going to be a min heap. And so this problem isn't actually too bad once you kind of understand what needs to happen. So we're going to have a min heap. We're going to take every single starting node from these lists. We're going to put them into the min heap in this way. So we're going to have the value and the actual node. And then we're just going to keep popping from the min heap. This is going to guarantee give us the smallest value. And then we're going to see, does this node have an X that we popped? If it does, put it back into the heap. And if not, put nothing back into the heap. And then once the heap is empty, we should have a complete merged linked list. So hopefully that makes sense. And let's try to code it up. Okay. So we have these lists, these are nodes, and let's just make sure. So k, we're given an array of k linked lists, each in sorted order. So this k can actually be empty. And so if it's empty, I don't think it's going to matter because we're just going to loop through these lists. And if it's empty, we'll just have an output of nothing. So first what we need to do is we need to make a dummy node. So this is really good for linked list problems. You want to make a dummy node, especially when you're doing a lot of rearranging. That way, when you pop off the head or something, you don't have an error because you have a dummy node. So we're going to do that. So we're going to say dummy equals list node, and we can just pass in nothing. Default value 0, next none. Now we can say our current node that we're at is the dummy node, and then we're gonna. So what we're gonna do is when we're doing this, like the current node, let's say it's gonna start here, but when we pop off a node, we're gonna say current.next is gonna be the node that we pop off, and then we're gonna update the current to be the node we're at, and then we can just keep say current.next whatever, and then so our current is gonna be the last node, but then we can just return a dummy.next because that's gonna be the first, that's gonna be the head of the linked list. That's usually what they want. So. Okay, so what we need to do now is remember we need to make a heap. So let's just make a heap. And then we need to loop through all of these lists, and we need to say if there is something there. So for list in lists. So this is a list of list nodes, I believe, that returns a list node. Right, okay. So for list and lists, let me just see, k. Yeah, so I believe to get, also, I think this list might be some other, so just say item. List might have, yeah, so list might be something specific in Python that we don't want to use. So for lists and lists, I think when we call this list, we're going to get the head. So what we need to do is we need to append it, remember, to the heap. So we need to do heap push heap, and then we're going to remember we're going to append a tuple, right? So it's going to be item.val, and then we're going to append the item itself. So let's just make sure that works, and then we'll just return none for now, but let's just see if that's how you actually access these list nodes. Okay, not greater item.val list node. Okay, so the problem is it looks like it's saying it's not supported. Okay, so I do believe that this is how you access this. This item would be the front item, but instead of, we can't pass in the node directly because there is no node comparison. So instead of doing that, let's change this code to for I in range len lists. Now we can say, so let's just make sure also list length. Okay. Okay, so let's just make sure that if lists I, this is the actual node, does not equal none, then we're going to add it to the heap, but we're not going to add the node. So instead of this picture where we add this, instead of the picture where we add the value and then the node, instead of that, we're going to pass the index. And then what we can do is, once we actually pop off the node, we're not going to pop off, we are going to pop off the node, but then we're going to update the node at the current index in this list to be the next of that node. So let's just show you what that looks like really quick. So let's say we have like this, let's say 2, 3 example. And let's say this is at index 0 in this list, right? So when we access L0, it's going to be this node. And then what we are going to do is, once we pop this node off the heap, instead of popping the node directly, what we're going to say is we're just going to say something like this: L0 equals L0 dot next. And then what that will do is, because this array starts off accessing the head element, now this L0 is going to be this instead. So instead of actually instead of actually getting these nodes directly on the heap, we can just keep saying, let's get the next one and the next one and the next one and update it, and then eventually we're going to be out of bounds here. So there will be a no node here. So that's what we're going to have to do here. So if less I does not equal none, like, okay, this might be some empty, this might be an empty node, and so then we're going to push to the heap. So here we can heap push, heap, and then we are going to have a tuple of, so it's going to be the value list I dot val, as we said before, but now instead of having the actual node, we're just going to do this because yeah, we can't compare nodes in a heap. So the way we could fix this, I think, is we can actually have a comparison operator in this list node. So if you want to try it that way, you can definitely do that. You can make a comparison method in this list node. But I think actually you're not supposed to have access to this list node, so I don't think you would want to do that, to be honest. Okay. So now what we need to do is this is our whole heap is full now, and so we can even print it just to see here. Heap, and let's just return none, but let's print the heap here. Okay, so we can see that. Let's take a look. So value 1 at index 0, value 1 at index 1, value 2 at index 2, that's what we wanted, right? So value 1, value 1, value 2. So that's what we wanted. So now what we need to do is we need to say while heap. That means we still have nodes left in the heap. Then we are going to be popping, right? So when we pop a value and an index, so we can just say value index equals heap pop heap. And then what we need to do is actually, I don't think we need this value. I don't think we're going to be using the value. We just need the index of the node we're at, and then we're going to need to append that to a array because we don't care about the value. We're going to be adding the node directly into our chain of nodes, right? So we have this dummy, and then it's going to have some nodes, and this is going to be our current node. And then when we need the next node, we're actually putting on the node. So we don't care about the value. That doesn't matter. So if we don't care about something, we can do this. And now we need to actually say cur.next. Yeah, so cur.next equals lists index here. And so this list index is going to be the current node that was in our heap. And now what we need to do is, now that we put in this node, we need to update it, right? So we need to say lists index equals lists index dot next. So that'll go to the next node at this current index. So like if we were at this 1, now it would be here in the list. When we say list 0, it would give you this second node. Okay, so we do that. Now we also need to say cur equals cur.next, right? Because in our picture, if we have this cur, so if we have a node with cur and then we put another node on here, now we want our cur to be the last node again. So then we can say cur.next equals something else in the future. And so now that this list index is the next node, now what we need to do is we need to see if it's none or not. And if it's not none, then we need to add this value to the heap again to see if is this going to be our minimum one. So if list index does not equal none, then we need to do this heap push. So heap list index, and then this is just an index as well. Okay, and so this is going to add the next node, and then once we are out of nodes. So for example, if we were here, if this is the node that we popped off, then we would add index 0 again, and then the value would be 4 into the heap. Okay, so we do that, then we don't want this return none. So I think, let me just double check. So we have this index, we have this cur.next. Index equals this index. I think now all we need to do is just return dummy.next, and that's going to be the first node. So let's just see if we have any errors here. Okay. Okay. So hopefully that makes sense with the way this list works. Is once again this array. This isn't a list of lists. This is a list of list nodes. And so what it really looks like is like for this example, it would be, if this is an array, this would be node with value 1, node with value 1, node with value 2, right? And that would be this value 1, this value 1, this value 2. And then when we say L0 equals L0 dot next, then it says, okay, go to this node. What is its next node? Well, its next node is 4. Then put that in. So now, instead of this 1, it'll be this 4 that has a next 5. Okay. So hopefully that makes sense. So let's do the time and space complexity for this problem. Okay, so what are we doing? So we're making a dummy node, which is nothing. This is nothing. This is nothing. Okay, so we are pushing every single node onto the heap. So not every single node, we're pushing the first node of every single list. And so our heap, or time-wise, this is going to take, if our, so let's just make another variable. Let's just say L equals length of lists. Okay, so time-wise, this is gonna take L time. But remember that when we traverse this heap, we do need to take every single node. And so this time complexity, we're gonna need to push every single node, and then we're gonna need to pop every single node. So it's gonna be, remember, for a push and a pop is log n, and so it's gonna be n log n, where n equals total number of nodes. That's going to be the time complexity. Okay, now let's think about the space complexity. So what data structures are we creating? We are creating a heap, but how many values will our heap hold at its maximum? So remember, our heap is going to hold only one value from each one of these sublists. And so if L is the length of these lists, like it's 3 here, the maximum storage from our heap is going to be L, because we can only have one value from each one of these lists. When we pop, then we can replace it with another one, but we're never going to have more than length of the total thing here. And even though we are appending these nodes on the dummy, we're not really creating anything else. We're just creating pointers. So that's going to be, hopefully that makes sense, that this is length of this list right here, and then the time is n log n, where n is the total number of nodes total. So like here it'd be 8 nodes and so on. Okay, so that's it for this problem. And if you like this kind of stuff, then like and subscribe, and I'll see you in the next one.